Nanonexus, and our topic is optimization in drug delivery using solid lipid nanoparticles. A solid lipid nanoparticle is a nano-sized carrier designed for efficient drug delivery. They consist of a solid lipid core stabilized by surfactant. They offer improved bioavailability, reduced dosage frequency, and greater therapeutic effectiveness compared to traditional delivery systems. In this paper, we will be focusing on optimizing drug loading efficiency in solid lipid nanoparticles for controlled and extended drug delivery profile through advanced chemical techniques. SLN is prepared in two stages. The primary stage gives rise to a very raw form of the SLN, while the secondary stage gives rise to a refined and stabilized nanoparticle. The parameters for primary production are based on two factors, the lipid and the surfactant. Coming to optimization of drug loading efficiency of SLNs by surface modification, mainly polymer-based surface modification. When we incorporate biodegradable polymers into SLNs, we create hybrid nanoparticles that control drug release kinetics and improve drug loading. Hydrophilic polymers like polysorbates not only enhance the stability, they are also effective for antioxidant skin delivery. Now, using the PSPIT technique, SLNs are synthesized by heating and cooling cycles that promote to microemulsion formation and nanoemulsion formation, which is followed by SLN precipitation at lower temperatures. These cycles not only reduce SLN size, they also create a hydrophilic coating, which enhances circulation and uptake after administration. The hydrophilic coating on SLN prolongs circulation and also enables targeted delivery through receptor mediation. Now coming to surface modification through chitosan coating polymer. Chitosan is a natural cationic polysaccharide and it is commonly used for surface modification. Its positive charge interacts with lipid carboxyl groups to prevent aggregation and it improves stability. It is very suitable for applications like oral delivery of anti-cancer drugs. Chitosan coatings not only improve the SNL stability in SNL environments, they also enhance the drug loading efficiency by maintaining SLN structure integrity, making these nanoparticles highly drug effective.
So starting with the preparation techniques, coming to the first one, which is high pressure homogenization. It is further divided into two types. Coming to the first one, hot HPH. In this method, the lipids are first heated above the melting points and then they are mixed with the drug to form a type of pre-emulsion. This mixture is then processed through a high pressure homogenizer. The advantage of using this technique is that it can be used for large scale production like in industries. And coming to the limitation, it is not suitable for heat sensitive drugs as it can lead to drug degradation and instability. Now, cold HPH, in this method, the drug lipid mixture is solidified by rapid cooling and then processed at low temperatures to avoid thermal degradation. It is suitable for heat sensitive drugs, but the limitation is that it produces a broader particle size range. Now, coming to the second method, which is solvent emulsification evaporation. In this process, the lipid is dissolved in a water immiscible organic solvent and then emulsified in an aqueous phase. After that, the solvent is evaporated and under the reduced pressure, which gives us nanoparticles as a precipitate. It is effective for producing small and uniform nanoparticles with sizes under 100 nanometer and low poly disparity. But the limitation is that it requires careful selection of the solvents for compatibility and phase management for consistency. Now coming to the third method, which is double emulsification. In this method, we form a water in water or oil in water in oil type of emulsion which can encapsulate both hydrophobic and hydrophilic drugs. It is useful for complex drugs like proteins and nucleic acids that tend to diffuse out of the single phase emulsions. The main challenge is to maintain the homogeneity and controlling the droplet size. Now coming to the next topic, which is stability challenges and solutions. So there are majorly four types of instabilities. The first one is creaming. It occurs when the less dense lipid phase migrates to the surface. This can lead to aggregation and coalescence. Then flocculation. It occurs when there are weak interactions between the particles which results in clusters. Coming to the third one, coalescence. It occurs when smaller particles fuse together to form larger particles, due to which the particles formed are less uniform in size and shape. and Ostwald ripening. In this, the smaller particles dissolve and redeposit onto larger particles due to the surface energy differences. Now, there are various techniques to enhance the stability. The first one is regulating particle size distribution. Then the second one is optimizing lipid and surfactant composition. The third one is maintaining zeta potential. And coming to the final one, by incorporating stabilizers. Now, the advantages of SLNs. It protects drugs from breaking down too soon into the body. Coming to the second point, it allows targeted and controlled release, which provides better delivery. Then it is made from safe substances, so it is not harmful for the body. Coming to the last point, it can carry many types of drugs, making it suitable for various treatments. Now, coming to the disadvantages, the particles can get larger due to instability, reducing its effectiveness. Second point, the drugs might leak out from the storage areas. Third point, SLNs can sometimes turn into the gel. Coming to the final point, we have to be very specific about the method of preparation while dealing with heat sensitive drugs.
I'll be covering the future aspects or the further topics that we'll be covering in the report. First up, we'll be covering drug incorporation. There are three different models to incorporate active ingredients into SLN. These are the homogeneous matrix model, drug enriched shell model, and drug enriched core model. The structure obtained is a function of formulation composition such as lipid, the active compound, the surfactant, and the production conditions. Drug-enriched outer shell can be obtained when the phase separation occurs during the cooling process from liquid oil droplet to the formation of solid lipid nanoparticles. The lipid can precipitate first, forming a practically compound-free lipid core. Also, during the forming process of lipid core, the concentration of the active compound in the remaining liquid lipid increases continuously. Finally, the compound enriched shell crystallizes. This model is assumed to give away a speedy release, which is highly desired in various SLN applications. The structure of SLN formed depends on the chemical nature of active compound and excipients and the interaction thereof. Next up, we'll be covering drug release from SLN. It has been observed through intense investigations that the release profile is a function of the production temperature. For the burst phenomena, it has been observed that the release phenomena only occurs when hot homogenization is used and very high temperatures are desired or applied. The release kinetics can also depend on the release conditions. Higher surfactant concentration can lead to higher burst release. Solubility increases drastically, and so does burst effect when increased temperature and increased surfactant concentrations are used. Next up, we'll be covering cancer therapies through SLNs. Recently, SLNs have found a wide application for the cancer treatment. Cancer is a condition where cells in specific body part grow and reproduce uncontrollably. Apart from a few cancer types, example breast cancer, for which hormonal therapy or immunotherapy is used, cytotoxic drugs are used as a primary form of chemotherapy for cancer. Due to their numerous advantages offered by SLN, this new drug carrier is considered as an emerging drug carrier system in the field of anti-cancer drug delivery. We'll be covering the treatment of tumor through SLN. As we all know, a tumor is usually associated with a defective leaky vascular architecture due to the poorly regulated nature of tumor angiogenesis. Recent studies have shown improved SLN uptake and accumulation in tumor tissue due to physiological tumor tissue characteristics such as abnormalities and dysfunctional tumor vasculature, which allow SLN in nanorange size to easily permeate the tumor. This is often quoted as the enhanced permeability and retention EPR effect. Furthermore, with the advances in surface engineering technology, the biodistribution of SLN can be further manipulated by modifying the surface physiochemical properties of SLN to target them to the tissue of particular interest. As a result, the chances of drugs reaching the tumor sites can be further enhanced and systematic drug toxicity can be reduced. These were the topics that we'll be covering for the next part of our report. Thank you.